Hello friends, welcome back to the mathematical room. I am the caretaker Lucifer. So today we are going to see functions. We already have seen, so this is the third section of the third chapter in Tao's book Analysis 1. So we already know about the concept of functions. In fact, we have been using it for a long time in our mathematical practices. But we know it somewhat informally. So informally functions are like this. Informally, a function f from a set x to another set y is an operation which assigns to each element, which is also known as input, x in x, a single element which is known as output. Y belonging to y, or we can write fx belonging to y. So we have already used this informal concept in the previous chapter. When we studied the natural numbers. So there we have already used this idea, but now we are going to look at this thing more formally, and the formal definition goes like this. So this is section 3.3, so this will be definition 331. Functions. Let x and y be sets. Let px comma y be a property pertaining to an element x in x and an element y in y, such that for each x belonging to x, there exists exactly one y in y for which this property is true. Okay, so we are given two sets x and y, and for an element from x and an element from y, x and y, there is a property. Okay, so for any given such choice of an element from x and an element from y, the property is either true or false. That's what we mean by the property pertaining to this choice of elements. But there is a condition, and the condition is that for every x, for every element x in x, there is exactly one element y in y for which this property is true. This is the condition. Then the function with domain x and range y defined by this property P is the object which given an input assigns a unique output, or let me say it like this, assigns an output fx in y. And what is that output? That output is defined like this, defined to be that unique element fx in y for which px comma fx is true. For which px comma fx is true. That is, or therefore, for any x in x and y in y, y is equal to fx if and only if px comma y is true. Okay, so this is the formal definition of a function, which is being defined by a property like this. Actually, I should have mentioned something else also here, which I have forgotten, but I will write it here. The thing is that the condition I should have written it here after saying what condition P satisfies. Okay, that condition has a name. The condition that for each x in x there is exactly one y in y such that px comma y is true is known as the vertical line test. Okay, I will explain what this means, but let us first of all look at the definition once more. So there are two sets given to us, x and y, and there is a property p which satisfies the condition which we have already seen. We have seen what this means. Then this property p defines a function f from x to y, where x is called the domain of the function and y is called the range of the function. In some texts, the authors call this second set codomain, but that's not what we are going to use. We are going to call this range. In analysis, we generally call the second set range. So the function has the first set as its domain and the second set as its range. Now it is going to be defined by using this property, or in other words, the property itself is defining the function. In what way? So the property defines the function as an object. What does that object do? That object assigns to each input x in x an output fx in y. And how is that output being determined? By p. Fx is defined to be that unique element in y for which px, fx is true. Remember that the condition p satisfies tells us that for every x there is exactly one y for which this is true, and that y we are denoting by fx to show its dependence on x, and that's what the function does. Now the use of this word object here should not be taken lightly. You see, so far we have seen two types of objects in our set theory. One is the natural numbers. Okay, so this is an object. I mean, these are objects in set theory, and that thing comes from the axiom of infinity, which says, besides the other things, that natural numbers are objects in our set theory. And by now we know the sense in which this word is used in set theory. When something is called an object, it has the potential to be an element of some set. So natural numbers are objects that we have seen from the axiom of infinity. Another thing is that sets themselves are also objects. That is coming from the first axiom in set theory, axiom 3.1. And this I think is the seventh axiom, right? Axiom 3.7. I may be wrong, but it's the axiom of infinity. Let me write that. That's where this is coming from, that natural numbers are objects. Now sets are objects, that is coming from the first axiom. Now additionally, this definition tells us that functions are also a kind of object. That means functions have the potential to be elements of a set. That we will see later on, but right now they are objects, and they are a function which is given by p is a particular object which behaves like this. So that if we choose any element x in x, the first set, and any element y in y, then y will be equal to fx if and only if px, y is true. Okay, now we come to this thing that I said I forgot to write here. The condition that p satisfies is sometimes known as the vertical line test. What does it mean? It's nothing very difficult. You see, the way we are saying p is a property. P may be any statement that involves x and y. So p may be something like this. X square plus y square is equal to 1, where x and y are real numbers, that is, our sets capital X and Y are both the set of real numbers, which we haven't seen yet, but we know what real numbers are. We haven't formally treated real numbers. They will come in the 5th chapter, but for now we know vaguely what real numbers are. So my P can be this. At the same time, with X and Y again R, I can have another P which looks like this. Y is equal to X squared. Now in this particular case, as you already know, there are figures which correspond to these equations in the two-dimensional Cartesian plane. The figure for the first equation is the unit circle centered at the origin. It's a circle having radius 1 and its center is at the origin. For the second figure, it looks like this. It's a parabola. Now the vertical line test says that if you draw a vertical line, okay, like this, any vertical line, then that line should intersect the figure that you are drawing for that given relation or given equation exactly once, or at most once. At most once, I should say. You see, in the second case, in case of this P, the vertical line is intersecting, any vertical line is intersecting the graph or the figure at exactly one point. So this is the vertical line test. So what it means is just simply this: for every x, there is exactly one y for which Px, y is true. Here, however, some vertical lines do not touch the figure at all. That is fine, there is no problem with that. But the thing is that there are some vertical lines which intersect the figure at more than one point. So this fails the vertical line test, because here for a given x, say this x, there are two values of y for which this is true. For example, if you take x equal to say 0, then you will be here. Then you have y equal to 1 and y equal to -1. Both of them satisfy this equation. So there the vertical line test is failed. Now P is not this kind of relation, P is this kind of relation. Then only we have a function. Okay, now next, there are some other names that we use to call a function. Let's just see that. Functions are sometimes called maps or transformations. Depending on the context. Functions are sometimes called, they are every now and then, functions and maps are used interchangeably, these two words. Transformations, however, are, this word is used in many places where we are thinking of a function as transforming one object, transforming x to y, or transforming x to fx. It's, in fact, in the way we know about functions, the informal knowledge that we have had always, that is that a function is like a machine which changes the input x and produces an output. So in that sense, a function is a transformation. However, this word is used more specifically in some higher parts of mathematics. For example, in linear algebra, when we study that structure known as a vector space, there we will come across something called linear transformations. A linear transformation is also a function, but a special type of function. But there is one more term that is sometimes used. Sometimes functions are also called morphisms. Okay, this also comes from algebra, but there are some, in every field there are structure preserving maps. We will see what they mean. They are known as morphisms. For example, in algebra we have homomorphisms. In topology we have homeomorphisms, but here is the thing. But to be more precise, morphisms actually refer to a much wider class of objects than functions, which sometimes may not correspond to actual functions. This also depending on the context. Sometimes morphisms are actual functions, but sometimes they are not. And to understand the situations where they are not functions, we have to know about category theory. Okay, but I don't know whether we will be able to study this in future, but we will try. Okay. In category theory, we study not just these mathematical structures like, for example, a group or a ring, or for example a topological space. In category theory, we consider the class of all groups, the category of all groups, category of all topological spaces, and relationships between categories. Okay, so that thing is there. So anyway, so let us now go to the first example of this section, example 332. Let x equal to n and y is also equal to n, means our familiar set of natural numbers. Now we define a property for x and y belonging to n, that is x belongs to x and y belongs to y. But in this case, since x and y are the same n, so we are taking small x and y to be two natural numbers. Let px comma y be the property this property that y is the successor of x. Okay, this is a legitimate property for given x and y. This is either true or false. For example, if we have 0 in place of x and 1 in place of y, then it is true. But if we have 0 here and 2 here, then this is false. So like that. Clearly, for every x in x, okay, we can write x. There is no harm in writing x. X is n, y is also n. For every x, there is exactly one y. There is exactly one y in y, which is also n in this case, for which p x comma y is true. Namely, y is equal to x plus plus. This particular value of y is the y for which px comma y is true. So that means our p is satisfying the vertical line test. Hence, we can use p to define a function, and the function is this. From x to y, that means it will go from the set of natural numbers to itself. Define a function given by we need to say what fx is. So this is a legitimate function that is being defined by this property p. Okay. For example, what does this function do? F of say 0 is equal to the successor of 0, which is 1. F of 2n plus 3 is equal to successor of 2n plus 3 is 2n plus 4 for all natural numbers n, etc. Okay. This function f is the increment function. We encountered in chapter 2. It takes a natural number as input and produces its increment as output. So this is the increment function. One may similarly try to define a decrement function. Say g from n to n, and g will also be given by a property. We have written try to define because we cannot define it. We will see what the problem is. By a property or by the property px comma y for x and y belonging to n, of course, this property y plus plus is equal to x. This is different from this one. Note the difference carefully. Here y is the increment of x. Here x is the increment of y. It's the opposite. Okay. Unfortunately, this property, this p means the new p, cannot be used to define a legitimate function g. Why? Because for 0 belonging to x, since our x is n, so 0, that natural number is also there. There is no y where? No y in y, which is also the set of natural numbers, for which y plus plus is equal to x. And why is that so? What we are saying here is that 0 is not the increment of any natural number. This is because of the third piano axiom. If you recall, the third axiom specifically says just this, that 0 should not be the increment of any natural number, so that we don't have any wrap around. If you recall those things. So it's from the third axiom, piano axiom, that we are getting this problem. However, keeping the, I cannot write keeping the same p. However, we can define a function h. Now we will not define it from n to n because 0 is giving us problem. So instead we define it from n minus 0. We are removing 0 from the first set to n. We can define a function by using the property px comma y for, let me write here, for x belonging to n minus 0 and y belonging to n. What is the property? The property is same, this one only. Y plus plus equal to x. Okay. Because of what? Okay, so what are we saying here now? If we remove 0 from the first set, then using a similar property which says that px comma y is true when y, the x is the successor of y. Using this property, we can define a function h. This is possible because of a result that we have already seen. If you remember, now these numbers I always forget. Lemma 2 to 10. So what lemma 2 to 10 says is that recall that while studying natural numbers, we came across a definition of positive natural numbers. We called a natural number positive if it's not 0. Okay, if it's a natural number that is different from 0. So this result says that for any positive natural number, there is exactly, say this is a positive natural number because we will be choosing x from n minus 0, right? So by definition x is a positive natural number. For such an x, there exists exactly one y which is also a natural number such that x